In this lecture, let us talk about magnitude comparators. The content of this lecture are as follow. First, we will talk about magnitude comparator. What are the magnitude comparators? Then we will discuss 1-bit magnitude comparator. Then we will move to the 2-bit magnitude comparator. Finally, we will discuss 4-bit magnitude comparator. Now, let us talk about comparator. What are the comparator? A comparator is a combinational logic circuit that compare the magnitude of two binary numbers or the binary quantities to determine which one number is greater, equal, or less magnitude. In other words, a comparator determines the relationship of two binary quantities. Suppose we have two numbers, suppose A and B. So these are two binary number. So the magnitude, so here is the input to number A and B. So the magnitude comparator will compare. So there could be three possible result. A could be greater than B. So the first possibility is A could be greater than B. A could be equal to B. And the third possibility is A could be a less than B. So this is the block diagram. So here this is the block diagram. So this comparator, n-bit comparator, it could be a 1-bit, 2-bit, 4-bit, up to 8-bit or 6-bit comparator, and so on. So this comparator circuit will compare two inputs A and B. So A could be a greater than B, A could be, so these are three possible outputs. A could be a greater than B, A could be equal to B, A could be less than B. Okay, now first let us talk about 1-bit comparator. In 1-bit comparator, we have two numbers A and B. These must have, for 1-bit comparator, these must have 1 bit. I mean, the number A must have 1 bit and B must have 1 bit. So there are three possibilities. A could be larger than B, A could be equal to B, A could be less than B. So first possibility, A could be less than B, A could be equal to B, A could be greater than B. Okay. Now let us draw its truth table. We know that we can describe our statement by a logic by truth table. So we have inputs A and B. Also these are 1-bit number. So these could be a 0 0, A could be 0, B could be 0. And another possibility is A could be 0, B could be 1, A could be 1, B could be 0, A could be 1 and B could be 1. So from this table we can see that A is, when A is greater than B, there are three possibilities. So these are the inputs. These are inputs. A and B are inputs. And here is we have output. So the first possibility, A could be greater than B. The other possibility is A is equal to B, and the third possibility is A is less than B. So in the first case here A and B are equal. So I can write when A and B are 0, so the output is equal. A and B are equal. So the other output would be 0. Say this circuit will compare and the result would be this output will be active. So in next case A is less and B is greater. So here I could incorporate 1. So this output would be 0, this output would be 0. So in this case A is greater than B, so I can write this output would be active high, the remaining would be low. So in this case again A is equal to 1 and B is equal to 1, so I can write A and B are equal. So I think here we have no need to use the K map for the simplification of this truth table. I can directly write it here. So suppose y1, I am writing here y1 in this when A is greater than B. So the output is y1. So y1 would be equal to, when y1 is equal to 1, so this min term I will write this min term. So in this case I can write the output y1 when A is greater than B. So in this case I can write A into B complement. So this is the output when A is greater than B. So in this case when A is equal to B, so I can write it as y2 when A is equal to B. So this can be written as A prime B prime, this min term A prime A prime B prime and A plus A into B. A into B. Now when A is less than B, so in this case I can write output y3 which is equal to A prime into B so this is the A prime into B. Now I can draw its circuit logic diagram. So its logic diagram would be, here I can draw the logic diagram. This is A, input A, this is the complement of A, this is A, this is the complement of A, and this is A. Similarly for input B, this is the complement of, sorry, I'm sorry, I'm not used to this digital board. this is the B complement and this is input B. So if I want to implement when A is greater than B, so I will use an AND gate. It has two inputs, which is A and B complement. When you want to use y2, which is the case when A is equal to B. So this is the I will incorporate a NOT gate with exclusive OR. So exclusive NOT gate, this can be described with the XNOR gate. So here, in fact, here I am not using the wiring. You guys are, you guys can connect these wires. So to avoid the messy, to avoid the messy, to mess this circuit, so I'm not connecting these wires. So so this is the case when A and B are equal. Sorry. When A is less than B, I can describe that by AND gate. With A complement and B. So I can write it A complement into B. So A complement will directly connect with this wire and B will connect with this wire, and A and B are will connect with this wire. B complement will connect with this wire. So now we have three outputs. This is Y1. This output will be active high when A is greater than B. This is Y2 and this is Y3. Okay, now let us talk about 2-bit comparator. This is the block diagram of 2-bits comparators. So here we have two binary numbers A and B. So the number A has 2 bits. Similarly, the binary number B has 2 bits. So this comparator circuit will compare A and B. So again you have three possibilities. A could be greater than B, A could be equal to B, A could be less than B. So okay, let us talk about its truth table. Suppose the truth table for 2-bit comparator. So here the number A, inputs A, and A is 2-bit, A has 2 bits. Those are most significant bit is A1 and least significant bit is A0. Similarly, B is 2-bit binary number with most significant bit B1 and least significant bit B0. So again we have two possibilities. A could be greater than B, A could be equal to B, A could be less than B. So we have a combination 0 0 0. So here we have 4 bits, so there will be 2 raised to power 4 16 combination. So I can write it 0 0 0 0 1 0 0 1 0 0 0 1 1 1 0 then 1 0 1 1 1 0 then 1 1 1. So the next combination is 1 0 0 0, then 1 0 0 1 1 0 1 0 1 0 1 1, then 1 0 1 1 0 0 1 1 0 1. Next is 1 1 1 0, finally 1 1 1 1. So there are total 16 combination 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. So in this case here this output is 0, this output is 1. For 0 0 0 A and B are equal, so here A and B are equal. So in this case A is equal to 0 and B is equal to 1. So I can write B is greater than 1. This output will be active and the remaining output would be zeros. And here again A is less than B, so I can write here 1. Again A is less than B, so here I can write 0 0 1. Okay, now in this case 0 1 0 0 A is greater than B and this output would be 0, this output would be 0. In this case 0 1 0 1, so A is equal to B in this case, the remaining output are 0. For 0 1 1 0 here A is less than B, because b is equal to 2 and a is equal to 1. So a is less than b, 0, 0, 1. Then next 0, 1, 1, 1, here a is less than b, so I can write it as 0, 0, 1. Okay, then 1, 0, 0, 0, here a is greater than b and remaining outputs are 0. For 1, 0, 0, 1, here a is greater, again a is greater than b, the remaining output are 0. 1, 0, 1, 0, here a and b are equal, the remaining output are 0. 1, 0, 1, 1, here a is less than b, so this output 0, a is less than b, this is 1. So 1, 1, okay, then 1, 1, 0, 0, here a is greater than b and the remaining output are 0. 1, 1, 0, 1, here a is greater than b, the remaining output are 0. Then 1, 1, 1, 0, here a is greater than b, remaining output are 0. And in final case 1, 1, 1, 1, a and b are equal in this case. So this output is 1, the remaining are 0. Now we will implement this truth table in Carney map. So Carney map will give us the simplified expression of the logic of the combinational circuit. So by using those simplified logical expression, we will implement a combinational or the logical circuit. Okay, now let us draw the Carney map here. Okay, the Carney map here is very simple. We can easily implement this truth table in the Carney map. So okay, now let us talk about the Carney map. Okay, the first case when a is greater than b, so there would be a 16 4 cross 4 16 boxes, and here I am saying a is greater than, for the a is greater than b, so here the inputs a1 and a0. This is the most significant bit is 1 b1 and least significant bit is b0. So first 0 0, zero 1, 1 1, here 1 0, then 0 0, 0 1 1 1 and 1 0. So first is the case uh, when A is greater than B. So here 0, A is 0, A naught is 0, A1 is 0, 0 0. So the output would be 0. So here A is 0 0 and B is 0 1, the output is 0. So we are considering the output when A is greater than B. So here you can, it is obvious A is less than B, A is 0 whereas B is equal to 3. Here again output is 0. So 0 1. So A is 0 1 and B is 0 0. So here A is greater than B. So I will plug in 1. And here 0 1, A and B are equal. So this is 0, 0 1, 1 1. This here B is greater. So I will put 0, 0 1, 1 0. Here A is less than B. So I will plug in 0. So here A is 1 1, A is equal to 3 and B is equal to 0. So I will plug in 1. Here A is 3 and B is 1. I will plug in 1. A is greater than B here. In this case A and B are equal. So I will incorporate 0 here. So here A is greater than B. I will plug in 1. For 1 0 0 0, A is greater than B. For 1 0 0 1, A is greater than B, and 1 0 1 1, here A is less than B. A and B are equal. So next let us talk about A and B are equal here. Sorry. So B1 most significant bit and B0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 and 1 0. So in this case, in this column, A is equal to B. A is 0 0 and B is 0 0. So I will plug in 1 here. Here B is greater than 1. So I will plug in 0. Here A B is greater than 1. I will plug in 0. Here B is greater than 1. I will plug in 0. So in this case 0 1 and 0 0, I will plug in 0. 0 1 0 1 are equal. So I will plug in 1. The remaining are 0. So here when A is 1 1, B is 0 0, I will plug in 0 because A and B are not equal. Here I am using those min terms wherein A and B are equal. So here A and B are not equal. Here it is obvious B is 1 1 and A is 1 1. So I will plug in 1 here. Here it's 0 or 1 0. Here it's 0 here it's 0, here it's 0, here it's 1. Okay, now let us talk about when b is greater than a. Here b is 0 1, 1 1 and 1 0. Here is 0 1, 1 1 and 1 0. So when a is 0 and b is 0, so this would be 0. So here b is 1 and a is 0, so this is 1. Here b is greater than 1, a, this is 1. Here b is greater than a is 0 0, b is 1 0, so I will plug in 1 here. Here a is 0 1, b is 0 0, I will plug in 0 here. So here I will plug in 0, a and b are equal. Here b is greater than 1, I will plug in 1 here. So here b is greater than a, I will plug in 1 here. So here a is greater than b, a is greater than b, a is equal to b, a is greater than b, I will plug in 0 here. Here a is greater than b, a is greater than b, a is less than b, I will plug in 1 here. So here a and b are equal. So now first solve this K map when a is greater than b. So in this case I can see that these 4 cells are adjacent. So these can be simplified. When we simplified these, so in this case I will get, by simplification, here I will get a naught, a 0 will cancel with this, a 0 and a 0 prime will cancel out, so I will get a 1, and here this b naught prime and b naught will cancel out, I will get a 1 and b 1. Right now, sorry, a 1 and b 1 prime. So here this is b naught, b 1 is 0. Next, these two terms are adjacent. Let me use some different color. Sorry, these two boxes are adjacent. So in this case, this a1 prime and a1 will cancel out, I will get a naught so I will get a naught and here I will get B naught and B1 prime and B naught prime. This is B1 and B naught, both have prime. So now this min term or this box is adjacent with this box. Let me use some different color. Yellow color. So this one is adjacent with this one. So here I will get A1, A naught, A1, A naught, A1, A naught, and here this B1 will cancel out with the B1 prime, so I will get B naught prime. So this is the expression for the circuit when A is greater than B. Now let us solve when A and B are equal. So in this case, no one term is adjacent or no one box is adjacent to other. So for this case, I can write it as y2 is equal to A1 A naught B1 and B naught. So all have prime, because here A1 is 0, A naught is 0, B1 is 0 and B naught is 0. So for this term I can write it as A1 prime A naught, B1 prime B naught. A1 A naught B1 and B naught. So here A1 is prime and B1 is prime. So A1 is prime, B1 is prime. Now for third term, this one, which is equal to A1 A naught B1 and B naught, and the final term is which is equal to A1 A naught prime B1 B naught prime. A1 A naught B1 and B naught. So here A naught has prime and B naught has prime. So this is the expression when A is equal to B. Now let us talk about this case. Here these four cells are adjacent, so I can write it as, so by simplifying I will get it here, A naught will cancel with the A naught prime, I will get A1, so Y3 is equal to A naught, sorry, this is equal to A1 prime and here B naught will cancel with B naught prime, I will get B1. So this is adjacent, this min term is adjacent to this min term, this min term is adjacent to this min term. So here by simplifying these two terms I will get this A1 prime will cancel out with A1, so I will get A naught prime and here this is equal to B1 and B naught. B1 and B naught. Okay, now this term is adjacent with, so these two terms, this term is adjacent with these terms, this can be simplified. So here I will get A1 prime, A naught prime and here B naught. B1 prime will cancel out with the B naught prime will B1 prime will cancel out with B1. So here I can write as A1 to A1 A0 and B naught. So A1 has prime and A naught has prime. Now I have three logical expression, I can implement it to make a logic diagram. Okay, now let us draw the logic diagram by using these logical expressions. So this expression can be further simplified. So I can write it as, here I can see in these two terms in these two terms we know that A1 prime and A naught prime, A1 prime and B1 primes are common. So A1 prime and B1 prime is common. So I will get A naught prime and B naught prime. So here I will get A naught B naught. So in this term I can get A1 B1, which is common. So A1 and B1 is common, so I will get A naught B naught plus A naught is the prime and B naught is a prime. So again here in these two terms, this term is a common, so I can write it as A exclusive not A exclusive NOR with B. A1 is exclusive NOR with B1 and A naught is exclusive NOR with the B naught. Now let us implement these simplified expression. This is for y2, this is y1. So here we have inputs, which is A1 and A naught, B1 and B naught. So I can make their complement, as I already in the previous lecture I already told you, instead of making complicated wiring, you can directly write their combination, make a combination circuit without wiring. So this is the A1 complement by adding a NOT gate. This is A naught complement and this is A naught. Similarly, B1 and this is the NOT gate, this is B naught and this is B naught prime. Here I will get B naught prime and here I will get B naught. So first let us implement y1. So we need a 3 AND gate and 1 OR gate. So for y1 output we need a 3 AND gate and we need 1 OR gate, which is 3 input OR gate. this is y1, and first AND gate has two inputs, which is equal to one input is A1 and the other input is other input is B1 prime. Okay, so this AND gate has three inputs, A naught, B1 prime and B naught prime. So first output is input is A naught, then B1 prime, here is B naught prime. The third AND gate has three inputs, A1, A naught and B naught prime. A1, this input is A naught and B naught prime. Similarly, you can implement the y2 and y3 you can implement in this way. Okay, now let us talk about 4-bit comparator. So let me erase this one. So this is the block diagram of 4-bit comparator. Here the binary number A has 4 binary inputs, 0, A0, A1, 4 binary bits, and the B has 4 binary bits. So this comparator circuit, this is the block diagram. So again we have 3 options: A could be greater than B, A could be equal to B, and A could be less than B. So you guys will try to solve this 4-bit comparator in your assignment. That's it, and thank you. Next we will talk about decoders and encoders.